me explain how carbon dating is supposed to work, and then tell you the serious problems with it. Carbon dating was not invented until 1949, in the last 60 years. So when they started telling the kids the Earth is billions of years old, back in 1830, they didn't tell them because of carbon dating. They'd never thought of carbon dating, never been heard of, okay? The geologic column is where it all started. We covered that on video 4 and some more on video 6 about the geologic column. The Earth was divided up into layers: Cenozoic, Mesozoic, Paleozoic, Archeozoic. Each layer was assigned a name, an age, and an index fossil. We covered that on video 4. Then they said, now we have to prove these layers are old. So they picked the numbers out of the clear blue sky, and any dating technique that comes along, like carbon dating or any other, has to match the geologic column or it's rejected. Only because the geologic column's been taught for 180 years now. So surely it's true. No, just because it's been taught 180 years doesn't make it true. But that's the logic those scientists will have. Well, we know the geologic column is established, therefore any carbon dates we get should match that. If they don't, we'll throw them out, and we'll keep testing till we do. They might have to test a sample 5 or 6 times till they get the number they want. Well, how do you know any of them are right then? If you're getting a different number every time, how would you know any of them are right? Radiometric dating would not have been feasible if the geologic column had not been erected first. Ever since William Smith at the beginning of the 19th century, fossils have been and still are the best and most accurate method of dating and correlating the rocks in which they occur. Apart from very modern examples, which really are archaeology, I can think of no cases of radioactive decay used to date fossils. They don't date fossils by carbon dating, they date them by their geologic position. That's how it's done. But here's what happens. Earth's atmosphere is about 100 miles thick. Space shuttle, in order to get free from friction, has to get up about 100 miles to be able to outside the air. And, you know, straight up, 100 miles is not that far from here to halfway to Tallahassee, you know. But if you go up, look at the atmosphere, it has very distinct layers to it, which is kind of interesting. It has a heat sink where it gets very, very cold, up about 7 or 8 miles up, like 80 or 90 or 100 below zero. But the Earth's atmosphere contains mostly nitrogen, 78% nitrogen, 20%, 21% oxygen, a little bit of CO2, for plants to breathe. Well, these don't breathe it, they're fake, but plants breathe in carbon dioxide. And there's a very tiny little bit of radioactive carbon-14, 0.0000765%. This radioactive carbon-14 is different than regular carbon. It's produced by radiation striking the sun, striking the atmosphere. Sunlight strikes the atmosphere, slaps the nitrogen around, and turns it into carbon-14. So it all starts by the sunlight hitting the atmosphere. Just to give you the procedure here, about 21 pounds of carbon-14 is produced every year, and that is spread out all over the world. If I told you there's 21 pounds of gold, but it's spread out equally all over the world, forget it. I'm not even going to go look for it. Okay? You're not going to find it. Real tiny amounts. If you look at a periodic table, carbon and nitrogen are right next to each other. Nitrogen has an atomic weight of 14. Carbon has an atomic weight of 12. But if the sunlight slaps the nitrogen around, it'll knock a few things off of it and it becomes carbon-14. So it still weighs as much as the nitrogen, but now it's considered a carbon. It's called radioactive, which does not mean it listens to the radio. It's just, it's unstable and it's going to break apart. It's like 3 guys dating the same girl. That relationship's not going to last, okay, forever. Something will go wrong, right? Carbon-14 is unstable. It does not like being carbon-14. It wants to get out of this situation, so it breaks down. About half of it will break down on a statistical average. About half of it is going to fall apart every 5,700 years. Now, it is doing this on a purely random procedure. I mean, you got a pile of molecules. You never know which one's going to fall apart. But statistics tell us about half of them will fall apart every 5,700 years, roughly. Now, while it is carbon-14, it's floating around in the atmosphere, like the rest of the carbon, and it latches onto oxygen, like carbon often does, and becomes carbon dioxide. And they hook up and they're happily floating around the atmosphere. And the plants are breathing in CO2. Animals come along and eat the plants. So the only way carbon-14 gets into the living world is from the atmosphere. It's produced by the sun, striking the atmosphere. Plants breathe it in, animals eat the plants. Probably during your lifetime, you've either eaten plants or you've eaten animals that have eaten plants. How many have ever done that before? Like today for lunch, right? Okay. Everything we do is from one of those two sources. It's plants or it's animals that ate plants. Well, the plants are absorbing CO2. Some of it is radioactive. So if the atmosphere contains 0.0000765%, it is assumed that the plants also have 0.0000765%. Probably a reasonable assumption, and I don't argue with them. I just point out this is one of dozens of assumptions that can enter in to really mess up things like carbon dating. So probably you have 0.0000765% carbon in you, because you've been eating these plants or you've been eating the animals that have eaten the plants. So probably it's all balanced in nature. When the plant or animal dies, it stops eating, stops taking in more C14, it stops breathing. Okay? Now whatever it had is going to decay. It was decaying while it was alive, but now there's nothing to replace it. So what they do is they compare the amount of C14 in the fossil with the amount in the atmosphere and say, wow, this fossil's only got half as much. Therefore, it's been dead for one half-life, 5,700 years. Because it continues to decay after it died, but now it can't be replaced. So while it was alive, it should have had about 0.0000765%. If it's only got 0.0003825%, it's been dead for one half-life, or two half-lives, or three half-lives, etc. In theory, it never goes to zero. But for practical purposes, you can't measure beyond a certain amount. You know, you're going to run out of stuff to measure. It goes from a half to a fourth to an eighth to a 16th to not enough to measure.